Assalamualaikum. My name is Muhammad Haziq Nur Hakim bin Sarudin. My matrix number is DE 2092. Today, I will present about introduction of our project. Okay, first, unbalanced fault in power system disrupt system stability due to deviation in fault currents and voltages. Second, negative sequence current and voltages from unbalanced fault cause mechanical stresses, overheating, power swings, and voltage fluctuation. Third, unbalanced fault impact voltage stability, leading to an imbalance, sag, swell, flicker distortion, and power quality issues. And lastly, external research aims to understand and mitigate unbalanced fault impact through techniques like symmetrical component analysis, simulation, and advanced protection schemes, with further research needed for enhanced system resilience. That's all from me. Thank you.
Hi, Assalamualaikum. My name is Alif Najmi bin Ahmad Tamizi, DE 220112. So, my part is to explain about the methodology of this project. So, firstly, the methodology section of a report outlines the report and technique used to conduct the study or research. It's a guide for reader to understand how the investigation was carried out and ensure transparency and reproducibility. So, as you can see the right, there are two figures, and first is about block diagram, and secondly is the flow chart. So the block diagram starting with unbalanced fault detection and protective relay system. So this is the main for our project. And next is a trip command and clearing, power system model, and stability analysis and control regulation. So for the flow chart, we start by construct a circuit in MATLAB software, and next and set the input value of block parameter in Simulink, and then the parameter is such as source, parallel RLC load, transformer, and fault. And next we run the MATLAB simulation and analyze the voltage, current, and power factor. Next, if the fault is still there, then we add protection scheme, have a return, and again analyze the voltage, current, and power factor. Then the final is make an analysis from the output result. So for the circuit project, we prepared two type of circuit. So the first one is the input parameter for each circuit remain the same, such as 3-volt, 3-phase source, 3-phase transformer, 2 windings, and also 3-phase RLC parallel load. So as we can see, the first circuit is to determine the output voltage and circuit for the system, and the below circuit is to determine the power factor of the system. And lastly, for this project, can give the output based on the tasks that have been given. So that's all from me. Thank you.
Bismillahirrahmanirrahim. My name is Muhammad Iman Aiman bin Muhammad Din. My matrix number is DE200077, and today I will present about the result and discussion for this project. So for the result, it is divided into two, which is the balanced result and the unbalanced result. So for balanced result, we can see from the simulation circuit, there is no fault block added into the circuit. And for the result, we divided it into two waveform, which is on the 11 kilovolt side and also on the 0.4 kilovolt side. So the voltage value for 11 kilovolt side is 8890.85 kilovolt, which is uniform for each phase. And then for the current on 11 kilovolt side, the peak value is 21.31 ampere, also uniform for each phase. And then we move to 0.4 kilovolt side. So for the voltage on 0.4 kilovolt side, the value of voltage is 323.25 volt, uniform for each phase, and also the current also uniform, which with the value of 20.20 ampere for each phase. And then the power factor that we calculated in the simulation for the balanced result is 0.7239, which is close to unity, which is unity is 1, so the system work efficiently. Next, we move to unbalanced result. So for unbalanced result, fault block is placed in the simulation. This is the fault block, and the switching time of the fault block is set from 0.02 second to 0.1 second. And we can see for the 11 kilovolt side waveform, on the time 0.02 to 0.1 second, which the fault occur, the voltage value drop to 0, and the current value increases, and the highest increment is 2688 ampere. So this phenomenon is typical in short circuit fault of power system. So the current increases due to low impedance path created by the fault. So for 0.4 kilovolt side, when the fault occur from the time 0.02 to 0.1 second, the current and voltage decreases nearly to zero because the fault occur on 11 kilovolt side, and without proper protection, the voltage and current will remain short circuit even though it flows through 0.4 kilovolt side of the power system. That is why the voltage and the current remain zero on the 0.4 kilovolt side. And then for power factor, for unbalanced result, the power factor recorded is 0.5418, which is lower than the power factor in balanced system. So this will result in less efficiency of the power system. And that's all from me. Thank you.
So, Assalamualaikum dan Assalamualaikum. My name is Muhammad Abdul Haris and my number is DE200057, and I'll present about the conclusion for our project. So, unbalanced faults in power system pose a significant threat to stability as they introduce voltage and current imbalance. These faults can result in voltage surge, unbalanced current, increased losses, and thermal overload in equipment, potentially causing system-wide instability. Maintaining power system stability is crucial, and unbalanced fault can lead to transient or dynamic instability, voltage instability, and frequency deviations. Through a combination of advanced protection and control technology, accurate modeling, and diligent planning, power system operator can minimize the adverse effects of unbalanced fault and maintain a stable and resilient power supply for consumer. So that's all from our group. So thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syafiq Aikal bin Suradi. My matrix number is DE200055 and I'm from section 2, group the volta voltage. So this is our group simulation. So we use MATLAB simulation, and then first of all the simulation, this is the 3-phase source block, and then this is the 3-phase VI measurement block, and then this 3-phase transformers, which is 2 windings, and then this the also the same 3-phase VI measurement, and then this the 3-phase parallel RLC load, and then this the 3-phase FAB, and then this is the scope. So firstly, for the 3-phase source, we use 11k volt, and then the transformers, we use step down, which is the parameter is firstly we use 11k volt, and then step down to the 0.4k volt. And then for the RLC load, RLC parallel load, we use frequency 50 Hz, and then the active power is 10 kilowatt. The inductive reactive power is 100 var, and capacitive reactive is 0. So for the 3-phase fault, we use fault resistance 0.001 and ground resistance 0.01. So we have to run it. So we done run it, and then go to the scope for 11k. So the scope show the graph, which is the graph is show the voltage sets of voltage. So this the for voltage, and then this below graph show for current. So for the voltage, it show the 11k. After we put the fault, it show the voltage set of the voltage, and then the current is unbalanced current. And then for the 0.4k volt, which is after the step down in this area. So it show the voltage set of the graph, and also the current have a set. So it show the voltage and current had unbalanced or not balanced current and voltage. So for the balance voltage and current, we have to remove the fault. So the fault are not in this simulation, and then we run it. So after we run it, we go to the scope. So it show the voltage and current in three phase is balanced. So it show after we remove the fault, the result graph, and with the result graph, voltage and current, it show the balance graph. For the 0.4 kV, also the same. The voltage and current are in balance after we remove the fault in the simulation. Besides, to balance the graph, we also have to we also should put the protection scheme into the simulation. So next, we have to measure the power factor. So for the power factor, we have to put the this block to measure the power factor of the simulation in this project. So we have to put the power factor block to display the power factor. So this the power CPS instantaneous block, and then this the product block, and then this the add block, and then this the square root block, and then this the divide block, and lastly this the display block. So after we put into the VI 3-phase VI measurement, we have to run it. So this is the value of the power factor when the presence of fault 3-phase. So this is the value of the power factor, which is 0.5418 PF. So lastly, we have to measure the power factor without the fault. So we have to delete the fault block, and then we run it. So we got the difference value of power factor, which is the value of power factor when there is no presence of fault. The value is 0.7239 power PF. So that's all for me. Thank you.